Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about FPN, short for Feature Pyramid Networks, that produce a feature pyramid for addressing the scaling problem in the object detection area. This work was published in the paper entitled as Feature Pyramid Networks for Object Detection in CVPR 2017. The outline of this lecture includes introduction about the purpose of object detection, the solution for detecting objects in multiple scales, and the main idea of FPN. Network architecture about the main components of FPN, including bottom-up pathway, lateral connection, and top-down pathway. Region proposal network about the brief description of RPN for generating rectangular bounding buses that possibly contain objects, and the way for adopting the FPN for object proposal generation. The task of object detection is to find out all objects in an input image. Formally, the input of object detection are an input image I and the set of object classes to be detected. For example, for this given image, we want to detect cat, dog, and duck. The outputs are bounding buses of the undetected objects and their class labels. The output of this example are the bounding buses of 4 detected objects and their class labels respectively. The two main challenges of the object detection are appearance variance and the scale problem. Appearance variance denotes that object appearances belonging to the same class are highly varied due to point of view or poses. As the cats enclosing by the rectangles, their appearances are highly varied. Scale problem means that object sizes are significantly different due to perspective phenomena. The objects near to the camera are large, but far objects are small. The Feature Pyramid Network (FPN) was proposed for mainly addressing the scale problem in object detection task. The basic approach for addressing scale problem is featurized image pyramid. For an input image, we firstly construct its image pyramid and then compute the features of the images at all pyramidal levels. After that, a model with a fixed size is used to scan overall featurized images and finally detect the objects with different scales. The detection of large object is from the upper pyramidal level. Small object is from the lower pyramidal level. However, the main drawback of featurized image pyramid is that it requires dense scale sampling to achieve good results, and thus have high computational complexity. Since the feature obtained from the convolutional neural networks has shown higher level semantics and thus more robust to scale variance. More recent, a single deep feature map from the less convolutional layer is used for prediction. This method is referred to as a single deep map. But more research reveal that pyramids are still required to get more accurate results. To alleviate this problem, the approaches called the deep feature hierarchy use the feature maps with enough semantics from the high-up layers for object detection. However, the high-up feature maps are with low resolution. This makes deep feature hierarchy approaches miss to use high-resolution maps that are important for detecting small objects. Accordingly, the main idea of FPN is to propagate semantics from the top layers to bottom layers, so as to produce a feature pyramid. The layers in the resulting feature pyramid are all with rich semantics and can be used for object detection. Next, we talk about network architecture of FPN. The input of the FPN is an image with an arbitrary size. The output of the FPN is a feature pyramid composed of multi-scaled layers that are all with rich semantics. The proposed FPN consists of three components, including bottom-up pathway, lateral connection, and the top-down pathway. Bottom-up pathway is for generating multiple scaled feature maps in a pyramidal shape. Lateral connection is to reduce channel numbers of all feature maps to a fixed size for further merging. Top-down pathway is to propagate semantics from topmost feature map to bottommost one. Here shows the network architecture of FPN in a schematic form. The bottom-up pathway includes all components inside the red rectangle. For an input image, the bottom-up pathway generates multiple scaled feature maps. After that, the lateral connection reduces the channel numbers of all feature maps to a fixed size for further merging in a top-down pathway. Finally, the top-down pathway produces a feature pyramid by propagating semantics from topmost feature map to bottommost one. Next, we will detail these three components. In general, bottom-up pathway is a backbone convolutional network composed of several stages. A stage consists of many layers and downsample the input feature maps by a factor of 2. In more detail, for a stage taking a feature map with size W times H as its input, it will produce a feature map with the size W over 2 times H over 2. For an input image, bottom-up pathway performs feed-forward computation and last produces a feature hierarchy with a scaling factor of 2. The feature maps at higher layers are with stronger semantics. The residual networks proposed in CVPR 2016 consists of 5 stages and is widely used as the bottom-up pathway for FPN. For a color image with the size 640 times 480, the residual networks output 5 feature maps in a pyramidal hierarchy with a scaling factor of 2. The channel numbers of these 5 feature maps are 2048, 1024, 512, 256, and 64 respectively. The detailed description of the residual networks can be found from our YouTube video named as Deep Residual Network via this link or the website. The function of lateral connection is to reduce the channel numbers of all pyramidal feature maps to a fixed value. For example, 256 used in this work. For a pyramid hierarchy from the bottom-up pathway, the lateral connection converts all feature maps with different channel numbers to the ones that are all with the same channel number equal to 256. For each feature map, lateral connection achieves the channel reduction via convolution layers. For a feature map with size W times H times D, the convolution layer uses 256 kernels for convolution operation. Each kernel is with the kernel size 1 times 1 times D and is applied for convolution with the stride size 1 by 1. Convolution by one kernel produces a W times H times 1 feature map. Convolution by two kernels produces a W times H times 2 feature map. Consequently, the output of the convolution layer is a W times H times 256 feature map. Finally, top-down pathway propagates semantics from the topmost feature map to the bottommost one by sequentially performing 2 steps from top to bottom. The first step is to upsample the upper feature map by a factor of 2 using linearist neighbor strategy. Then, the second step is to merge the upsampled feature map and the lower one by element-wise addition. In this example, we firstly upsample the topmost feature map by a factor of 2, and then merge the upsampled feature map with the one from lateral connection by element-wise addition. Again, we upsample the resulting feature map and merge it with the one from lateral connection. Repeating upsampling and merging until to the bottommost layer, we finally achieve semantics propagation and obtain a feature pyramid. The feature maps in the resulting feature pyramid are all with rich semantics. Furthermore, to reduce aliasing effect from upsampling, the top-down pathway performs 3 by 3 convolution with pending size equal to 1 for all feature maps. Next, we will talk about how to adapt the FPN to a network called the RPN, short for Region Proposal Network. RPN was proposed in 2015 and is a network widely used in two-stage object detection. The main idea of the RPN is to generate object proposals by using dense anchor mechanism. It attaches 9 anchors, including 3 aspect ratios and 3 scales, centered at each point of the convolutional feature map. For proposal generation, it predicts one proposal with 6 parameters, including 4 regression parameters and two parameters for class probabilities with respect to each anchor. Here shows the processing flow of RPN. For a convolutional feature map obtained by a backbone, for example VGG16, we attach each point with 9 anchors in 3 different aspect ratios and 3 different sizes. Then, RPN predicts 4 tuple regression of set and 2 tuple class probabilities for each anchor. In other words, RPN predicts 9 times 4 regression of set and 9 times 2 class probabilities for 9 anchors at every point. Accordingly, the output of RPN is a regression of set map with 36 channels and a class probability map with 18 channels. Let's further look into RPN architecture, which consists of 3 convolutional layers. The intermediate layer is to convert the input convolutional feature map to the one specifically for proposal generation. It firstly packs the feature map with 1 pixel and then perform convolutional operation by D kernels with the size 3 by 3, where D is the number of channels. This results in a feature map for predicting proposal parameters. After that, regression layer predicts the box parameters of all proposals by using 36 kernels with the size 1 by 1. Classification layer predicts the object background probabilities of all proposals by using 18 kernels with the size 1 by 1. You can find a detailed description of RPN from our YouTube video named as Region Proposal Network via this link or the website. Next, we detail the way for adopting FPN in RPN architecture. The modification of RPN for adopting FPN is anchor assignment. In RPN, each point at a single scale feature map is attached with 9 anchors in 3 different aspect ratios and 3 different sizes. The reason for using 3 different sizes is to deal with the detection of objects with multiple scales. Since the feature pyramid produced by FPN is composed of multiple scale feature maps, we attach 3 anchors that are different in aspect ratios but with the same size. For example, each point at the topmost layer is attached with 3 anchors. Layer aspect ratios are 1:1, 1:2, and 2:1 respectively, but sizes are all the same and equal to 32 square. Similar to the next layer, the attached anchors are all with the same size, equal to 64 square. Similarly, the sizes of the anchors for the last layer are all 512 square. Since the feature maps from FPN are all with rich semantics, the parameters of the RPN are shared across all feature levels. More specific, all layers from top to bottom use the same convolutional kernels in intermediate layer, regression layer, and classification layer to predict the regression parameters and class probabilities. For the topmost layer, RPN predicts 12 regression parameters and 6 class probabilities for 3 anchors. The same RPN is for the second layer until to the bottommost layer. In this video, we introduce a FPN feature pyramid network for producing feature pyramid by propagating semantics from the top layers to bottom layers. The layers with different resolutions in the resulting feature pyramid are all with rich semantics and can be directly used for detecting objects in multiple scales. This naturally addresses the scale problem in object detection task. Thanks for your listening and have a nice day.